In this video, we're going to look at one of the most confusing and probably the most important feature of a scope, which is triggering. I'm going to introduce you to first the normal mode and then the power of the auto mode for triggering. We'll look at how we adjust the level and what that means, and then looking at rising and falling edge triggering. And we'll see that the scope actually can look back in time and how it can do that. And then we'll talk real briefly about some of the other triggering features, and I'll tell you why I strongly recommend, unless you have a strong compelling reason, never use single mode. I can't tell you how many times I've found unusual signals that were completely unexpected because I was paying attention to the signals as they were coming in and never used the single trigger mode. Let's take a look at playing with the triggering on our AD2 scope. In order to explore this very important topic about the trigger, we're going to use a square wave signal from the waveform generator. So we've got it connected up just like we had in the previous video. We've got the plus input to channel 1 connected to the output of wave generator 1, and we've got the minus input on channel 1 connected to ground. And that's it. We're setting up the wave generator as a square wave, really simple, kilohertz, 1 volt amplitude, so it means it goes up 1 volt, down 1 volt, peak to peak of 2 volts. And we're going to turn it on, and it's running right now. Let's go to the scope and we'll take a look at it. And to activate the scope, if we haven't already, we have to turn it on. Right now it's in the stopped mode, so it's not triggering. When we turn it on, now we're triggering and we're looking at that signal in real time. The time base, millisecond per division and half a volt. And so it's real reasonable settings. We have 1 millisecond per division. That means, okay, here's our 1 millisecond period, and we have half a volt a division. So it's up 1 volt, down 1 volt. Now while we're here, real quickly about the vertical scale, you notice there's a little orange caret on the side here. If we grab hold of that caret and we just drag it up and down, we can change where the 0 point is. The 0 is up here. That's useful if we're looking at positive signals and we want to see them full scale. I can move this down. Or if I want to offset a signal and look at a small DC level on top of a large level, like looking at noise on the power rail, I would use an offset. And notice that as I move that caret, look way over here, when we set up the vertical scale, we had been paying attention to the range. That's how many volts per division. But there's also another number, which is the offset. This is the location of where that caret is on that screen. And notice as I move the caret, look, that offset changes. And so here we are at 1 volt. And basically that means, remember, here's the scale. It's a half a volt per division. Normally that 0 is in the middle here. So if I have an offset of 1 volt, that means the 0 location is now going to be positioned where 1 volt normally is. So here we are when it's 0, 1 volt is up here. If I offset by 1 volt, that means the 0 is going to be located at this location now. And I move it up here, and there's a 1 volt offset. If I want a minus 1 volt offset, in other words, I want to move that caret to where minus 1 volt normally would be on this scale, 2 divisions down, there's our 0 position, minus 1 volt. I'm going to keep it in the center here because we're looking at a signal that's plus and minus. I'll keep it the 0 centered in the middle of the screen. And on the other side, on the right side, there's another caret, and that caret is related to the trigger. All the trigger features that we're going to use are located in the top bar above the waveform. We'll walk through them real briefly, and then we'll talk about the difference between the auto and the normal mode. So this is single. Again, rarely use this button. You might think, oh, I only want to see a signal once, or I just want to freeze the screen. I'll just use single mode. And so that will stop the triggering, and it freezes the waveform. If you have to freeze that waveform in order to see it by using the single button, then you're not triggering correctly. If you have any kind of repetitive signal or any kind of signal that you know what to expect, you can always use trigger in order to see it. Never use the single function, because when you do that, you're freezing the scope. I'm not taking any measurements now. There could be some unusual behavior our device is generating coming in, and I'm not able to see it. That's why you always want to use triggering in order to see those waveforms. There are so many situations where we get unexpected, that means couldn't have predicted it, behavior from a device under test. We always want to see as much of the data as we can all the time. We don't want to stop the acquisition because Murphy's Law says when it's stopped, that's where the interesting stuff is going to come in. So unless you have a strong, compelling reason, never use the single trigger button. That freezes the last trigger, freezes the signal on the screen. If you have to resort to using the single button in order to see what's on the screen, you've admitted defeat that you were not able to get the triggering to work. Always work first on getting correct triggering. So let's turn our scope back on. We're triggered now, and now we see the different modes. Forget the repeated. We're always going to keep it on repeated for now, as long as we're looking at a short time base. But it's the auto versus the normal that we're going to adjust. So for now, we'll keep it on auto. The source is telling us where are we going to get that trigger signal from. We got channel 1 or channel 2. There are other places as well. And the condition is really about the slope. Is it a rising or falling edge? And the level is the DC level. Our scope is always looking at the voltage coming in. It's always measuring that signal coming in. It's just not always displaying it for us on the front screen. Those measurements that are coming in based on the sample rate as displayed up here, this is now we're sampling at 800 kilosamples per second. Those measurements coming in are going into a buffer. It's a circular buffer, and it's 8,192 elements long. And so it's constantly going to that buffer. And while it's going in, the trigger signal, the trigger circuit is looking at that input voltage. If that voltage goes above the level we set with a rising edge, then we're going to immediately display at that instant of time when we get that condition, we're going to display that waveform. And that's what we're doing right now. If I expand this scale, it's a little hard to tell because we got a pretty darn steady signal. But suppose we have some noise on top of it. Let's turn on the noise so we can see something changing here. Now you can see, hey, that signal is really changing, but we're triggering right here at this point. We have it set for 0 volt DC level with a rising edge. Where does that signal cross 0 volts with a rising edge? Right here, and it's rising edge, and that's where we're going to trigger. If we set the condition to be not 1 volt, but half a volt, for example, then we're going to trigger at this point. So we'll turn it on, and here is the 0 time. That's when the trigger comes in. We're triggering at that point. A little hard to see that unless we expand the time base. Let's do that a little bit. Let's zoom out on the time base. Zoom out on the time. Now we're beginning to see some of the signature of that noise. We zoom out on the time base. We zoom out on the time base. I don't know what the rise time of this signal is. We'll take a look at it. Here's some microsecond of division. So as soon as we get a rise time that is shorter than a microsecond, a little flag should go off in your head, and that says, uh-oh, the way we probe may influence the quality of the signal that we see because our rise time is shorter than a microsecond, so we want to be careful interpreting the measurements. And here we are at 200 nanoseconds of division. And you notice, it's not such a great square wave. It's got some distortion to it. Hard to tell, is that real or is that about the probing because it's shorter than a microsecond of division. We're going to see ways of distinguishing that a little later. But now we can see a little bit of feature on the edge. If I change my trigger level, look what happens. Where I cross the 0 is influenced by the trigger level. Now I set the trigger level for 0, and look, that's where t equals 0 begins. And if I say, okay, I want to trigger at this voltage level, t equals 0 begins when the signal crosses that DC voltage, and this tells us crosses it going up or crosses it going down. We have it set for rising. If we switch it to falling, where do you think it's going to switch? It's going to trigger at this DC level, but going through a falling edge. Let's look at the falling edge. And sure enough, here's that falling edge. Here's the DC level. That's when t equals 0 begins. So 2 conditions to trigger. It's not changing when we're taking data. It's changing when we're displaying that data on the front screen. Let's go back and look at the waveform on a expanded scale. So here's our waveform. We see the noise on top of it, so we know that we're taking data in real time. Let's go back to our rising edge, and we'll move the cursor to the center. So we're looking at a 0 voltage threshold, rising edge. That's when the scope is triggering. And if we have a repetitive waveform, then the wave looks like it's standing still. It's a repetitive waveform. It's always being triggered at the beginning of each cycle. And you can go back and look at other waveforms from the function generator. If we look at a sine wave, again, it's a repetitive signal. We're always triggering when it goes through that 0 point on a rising edge, and so every cycle looks the same over and over again, except of course for the noise. That's what's random, and we see that varying all over the place. Right now, we've been in the auto mode. I'm going to switch it to the normal mode, because normal, as the name implies, normal mode is the normal mode of triggering. That means that the scope is only going to display the waveform when that voltage threshold crosses that DC level, and in this case in a rising signal. It's going to trigger it right here. But suppose that and of course as I change the DC level, move it up, I'm displaying the data. I'm still taking the data all the time, in this case at 4 million samples per second. I'm still taking that data, it's going to a buffer. I'm just not displaying it unless the signal coming in crosses that threshold value in a rising edge. And so I'm going to display that waveform, whatever I've got in the buffer, I'm going to display that at that instant of time when it crosses that threshold. And because this is a buffer, I've gotten data back in time, I'm able to see, hey, what was coming beforehand? Because all that data is always going into a buffer, a first in, first out of shift buffer, a circular buffer, and I can look back in time. But suppose I don't get a valid trigger signal on channel 1. Suppose I adjust my DC level so that it's way up here. I don't have a valid trigger signal, and so in normal mode, I'm not triggering. I don't see any of the waveforms coming in. I'm still taking the data, it's going to the circular buffer, I'm just not displaying it. And this is sometimes a little confusing, because if I have the normal mode set, and my trigger level is above where my signal is coming in, then I'm not going to see anything sometimes. I'm not going to know if I have a signal coming in unless I adjust that trigger level. And as soon as I bring that trigger level within a range in which that signal is actually crossing, then I'm going to trigger in normal mode. And I can trigger any of these signals coming in as it crosses this DC level as I change the trigger. But if I change that level outside the range my signal is crossing, I'm never going to trigger. And if I don't know anything about the signal and I don't see anything coming in, sometimes I'm going to be confused. Do I really have something coming in? Do I have something connected in there? Or is it really I'm in normal mode and my trigger level is higher or lower than any value the signal is going to see? And so here is a trick we use. Instead of normal, we use auto. Auto does exactly the same thing normal does. In other words, it looks to see, when's the signal crossing that DC level, going up or going down, and then it's going to trigger. But if it doesn't see a trigger, a valid trigger level, within about a second or two, it's going to trigger anyway and just show you what's coming in. So when we switch to auto, we wait about a second or two, and now we're triggering. If we get a valid trigger level, so here we are, it's going to behave just like the normal mode, and we'll change the level, the time at which we're triggering, based on passing the DC level and going up or going down. So if we go to falling edge, we'll trigger on the falling edge going down. So in auto mode, we're doing normal triggering as long as it's a valid trigger level coming in. But if we set our level above the range in which the signal is actually crossing, if we wait about a second or two, that's a part of a parameter that's set, then we're going to trigger anyway. And that at least lets us see the signal coming in. Now, we don't see that steady pattern because we're not triggering based on the waveform coming in. We're triggering on time. We take a reading, we display it, and if we're in auto mode and we haven't seen a valid trigger, we're just going to take another reading. And so it's kind of arbitrary when that next reading comes in, and so we see this pattern that's moving all over the place. That's the value of auto trigger. It does exactly the same thing normal does, but if we don't know what that voltage level is and our switching and our triggering level is above or below the range of any voltage coming in, then we can still see something. And so when you're starting out, when you turn on the signal for the very first time, it's always a good idea to use auto because that absolutely guarantees that you're going to see some signal coming in. And once you know the signal coming in, now you can adjust the threshold of where you want to trigger. It's also important to keep in mind that I have noise turned on, but that's not the voltage that's going into the buffer that's being used to do the triggering. What's going into the buffer used to do the triggering is the average value. And so I can't really trigger on that high frequency noise on this scale. So if I try to do that, I come up here, I'm trying to trigger on that noise, I just can't do it. I got into the trigger anytime kind of mode, and I'm at 50 millivolts above the level. If I go to 1.01 volts, so 10 millivolts above the level, again, I'm not triggering. I don't see that noise because that's not what's going in the buffer. It's the average value that's going into the buffer. So at this point, you should play around with the different waveforms, play around with the trigger settings. Always start out on auto and then you can switch to normal. The advantage of normal is if you've set a voltage level and you're waiting for an event to come along that exceeds that voltage level, and that's what defines your event, then you can capture it in normal mode. And we'll see examples of that later on. So at this point, you can play around with the settings, get comfortable with the auto, normal, the rising, falling, and the threshold level.